All right. I think we now have a working stream. Going to just cross-post the link back into the classroom, and hopefully that will work. And then we can get started. Okay, so I posted that up in the classroom. Hopefully we'll get some people coming in shortly. In the meantime, thank you for your patience. See, we're up to 3 viewers now, so it should be pretty quick. And hopefully it stays connected. It's a bit of a weird one. My internet was continuing to work fine, and it was specifically the connection to YouTube didn't seem to be doing so well. So we will do the best we can under those circumstances. 5 people in, excellent. So I'll give it maybe another 30 seconds or so, and then we'll get started. So welcome to those of you who are just joining. Welcome, folks. Backwards. All right. Okay, so hopefully other people will join in over the next little while. Today we're going to talk about distributivity by monomials. And because we haven't been in class, we haven't really talked about what a monomial is. And it's a really big fancy word for a very simple thing. A monomial is simply, I'll give you some examples here. A monomial is simply any number or any variable or any multiplication of numbers and variables. So 3 is a monomial, x is a monomial, 3x is a monomial, 3x squared, which is 3 times x, is also a monomial because it's a multiplication of a number times a variable times a variable. Negative 17.4 x squared y cubed z is also a monomial because it's a number, negative 17.4, times a variable, x, times a variable, second x, times a variable, y, times times another variable, y, times a third y, and then times z. So it's a multiplication of numbers and variables. So all of these things here are monomials. And so we're going to look at how do we do distributivity if the part on the outside of the brackets is not just a number, but is in fact a monomial. All right. So I've got some examples set up here. It's still backwards on my screen. Excuse me, but hopefully right side up on yours. So we're going to start with stuff that we're familiar with. So if you remember way back when we were still in the classroom, we talked about exponent rules. And we said x squared times x cubed. And we did it the long way at first. We said, well, x squared is x times x. And x cubed is x times x times x. So together, that is x times x times x times x times x, or x to the 5. And then after doing this a few times, we notice a pattern, which is that the exponents can be added together to get the final exponent. And so 2 plus 3 is 5. And we found that it made sense that this would always be the rule because the exponent counts how many x's are multiplied. It's a counter for multiplication. So a 2 in the exponent means there are 2 x's being multiplied. 3 means there's 3 x's. Put all of those together in a big multiplication, and we're going to have 5 x's. So now let's take a look at a slightly more complicated one. We have 3 times x squared times x cubed. Well, there's an invisible 1 here in front of the x cubed. And when we're multiplying a bunch of stuff, we can choose what order we want to multiply things in, right? 2 times 3 is 6. 3 times 2 is also 6. The order doesn't matter. So here we can do 3 times 1. That's going to be 3. We can do x squared times x cubed. That's going to be x to the 5. And now we have it simplified down to a single number and a single variable part with exponent. So this is getting us thinking about a monomial times another monomial. And let's look at a slightly more complicated version of that. So here we have 3x squared times 4x cubed. Well, again, we can do whatever order we want. So we're going to put the number parts together. 3 times 4 is 12. X squared times x cubed is 5. All right, so I'm going to pause it there. If you have questions, you can ask them in the chat. I'm going to continue to make some observations while we wait for that. And mostly back the very first week of class, I think I told you that one of the hardest things about grade 9 was knowing the difference between multiplying and adding. And this is another example. Let's get our autofocus going here. This is another example of that, right? We're doing a multiplication, monomial times monomial. We need to remember that that means we're multiplying the coefficients, the numbers out front, but we are going to be adding the exponents because exponents count multiplications. So if we do more multiplications, that's the same as adding the exponents. Sense to you? Thank you, Nina. Is it better now? It did blur up for a moment there, but hopefully it's sharp. So if you're seeing blurry screen, if you can just put a 2 in the chat. And if you're feeling good about what we've done so far and ready to move on, if you can just put a 1 in the chat for me. So 1 means ready to move on. 2 means I'm seeing a blurry screen. Oh, Jackson's seeing blurry as well. Okay. So again, 1 means ready to move on. 2 means blurry screen. Alan, Aiden, getting blurry screens as well. All right. Emma and Jordan, are you seeing the screen clearly? Okay, thank you, Alan. All right, if there's anyone who's still seeing it blurred, just put a 2 in the chat for me. Nina, is it better for you? Thank you, Jordan. That's good to know. Thank you, Emma. Oh, it's still blurry. Interesting. Huh. That is super confusing. I'm not sure why some people would see it blurry and some people would see it clearly. Okay, so I apologize. What I'm going to try and do is just write larger and hope that that's enough to deal with the blurriness. And I'm hoping that YouTube is recording a clear version, so if you do need to come back afterwards, you'll be able to see it clearly. But I'm going to write them larger for you so that hopefully even through some blur, it's okay. So our next one here is 3 times 2x minus 4. And Nina, Jackson, and Aiden, if you can let me know whether you're able to read that or not, that would be really helpful. Just post it in the chat. I'm going to keep moving, but I'll watch for your comments. So this is a standard distributive property question. We have a monomial out front technically, but it's just a number. So it's one of the simplest monomials that we can have. And we already know how to do this when it's just a number out front. So 3 times 2x is going to be 3 times 2 is 6. X just stays x because there's nothing to multiply it with. Oh, good. Thanks, Nina. And then 3 times negative 4 is negative 12. So straightforward. This reminds us how to do our distributivity. We take whatever's out front and we multiply it by each of the terms in the brackets. All right, we're going to take a look at our next one. So that's example 5. Example 6. We're going to start to get a little complicated here. So for example 6, we have 3x squared times 4x cubed plus 2. So this is our first example where we have a full complicated monomial out front. We have 3x squared. It's got a number part and a variable part. And so we're going to follow the same idea we did earlier. Oh, refocus, there we go. Follow the same idea we did earlier about multiplying what's out front times each of the terms. So we're going to have the whole 3x squared times the whole 4x cubed, and also times plus 2. And so that means we're going to get 3x squared times 4x cubed plus 3x squared times 2. So I'm just showing what multiplications we're about to do, how the distributive property distributes 3x squared to both terms of the original here. So now we can go and do this multiplication. Well, remember we said with multiplying, you can multiply whichever parts together first that you want, if it's one big multiplication like this. So we're going to do that. 3 times 4, that's the easy part. 3 times 4 is 12. And then x squared times x cubed. Well, for exponents with the same base, we add the exponents to get the final answer when we're multiplying. And there we go. All right. So then for the second part, we have 3 times 2, which is 6, and then x squared. All right. So as usual, if you have questions, feel free to put them up in the chat. But here you can see how we did our distributive property. And the key is really to remember that number times number is just normal multiplication. But variable times variable, we're adding the exponents together. All right. Show me a 1 in the chat if that's making sense to you so far. Good question, Jackson. Yes. We just follow the same procedure. We do the distributivity. I like to show the first line as showing the multiplications, and then on the second line do them. Thank you, folks. Seeing lots of 1s in the chat. Once we get good at it, it is totally reasonable to go from the first line to the result. But for now, you might find that it's easier to do this multiplication. All right, hold on one moment. Got a call coming through. Can you answer that, Julie? Okay, folks, we're going to take a 5-minute break. I'm getting a call from the hospital where my dad is, and so I need to take it. So my apologies for that. I'll be back as quick as I can. All right, my apologies, folks. We have had an interruption that I'd hoped we wouldn't have, but we will keep things going. I know it's a bit weird for me to step out in the middle of this, but as I mentioned, my dad's in the hospital. He had COVID-19, but the doctor just called to actually say that he's tested clear and he's in good health. So excellent news for me. And I'm ready to get back to the lesson. Okay, so here we go. We've got this more complicated one. Walked through it, saw a bunch of ones in chat. It looks like people are feeling pretty okay with it. So we'll move into a few more, or I guess one more, just because it's a bit of a special case, and I want to make sure that people know how to handle this special case. So if we have 2x times 3x plus 4, something like that, then the reason that this is a special case is that we are not showing the exponents on the x's. And so a lot of times for something like this, people might assume, oh, if there's no exponent on the x, it's just 0. That's not the case. If there's no exponent, it's like an invisible 1. And we need to treat it that way. So if we go 2x times 3x, so that's the first part of the distributivity. And then the second part plus 2x times 4. So you can see 2x has been distributed to both parts in the bracket, both terms in the bracket. And then we can do these multiplications. 2 times 3 is 6. X times x is x squared. Plus 2 times 4 is 8. X, well, there's nothing to multiply it with, so it's just going to stay as x. Thanks, Jordan. It is indeed very good news. I'm very, very happy to hear it. Okay, so that is the main idea here. We're going to do one more, and there's not really anything new in terms of techniques here, but I just want to show you how this monomial distributivity can fit in with some other collecting like term skills. And before we do that, we're going to answer Jackson's question, which is how would you do x times x plus 2? So the key here is to just fill in any missing numbers. So if there's no number in front of the x, what is it? It's a 1. If there's no exponent on the x, what is it? It's a 1. Same thing here, no numbers. They're going to be 1s. And that's the important part, is to know, hey, it's not 0 if there's no number. It's usually a 1, which is the case here. So now we can show the distributivity. Multiply the pieces together, plus 1x to the 1 times 2. My apologies if that's getting a bit small. So 1 times 1 is 1. X to the 1 times x to the 1. It's not multiplying the ones, it's adding them because they're exponents. 1 plus 1 is 2. And then we do the second half. 1 times 2 is 2. X to the power of 1. There's no other x's to multiply it with, so we just get x to the power of 1. And then some of these things we don't need to write. So usually we wouldn't say 1x squared, we'd just put x squared. We wouldn't put plus 2x to the 1, we'd just put plus 2x. And so x squared plus 2x would be the final result for that. So usually when we do a question like this, we don't actually write in all the ones. Once you get used to knowing that they're there, then you can do it without actually writing them in. But in the meantime, and especially if you do a question and you find that you have it incorrect by checking in the back of the book, try putting in the ones and doing it with the ones there and see if that helps you. Okay, so let's do the last example so that you can see how distributive property mixes in with some collecting like terms. So the questions will usually ask you to simplify. And remember, if we have an equation with an equal sign in it and an x, we can often solve it. But if we have an expression with no equal sign, then usually the most we can do is to simplify it, to make another expression that has the exact same values, but is simpler to write. So here we're going to simplify 5x times 6x minus 7 minus x times 5x plus 2. So it's longer, it's more complicated, but there's nothing new in terms of what we need to do here. It's all the same steps that we've done before. Key thing to remember, wherever the bracket ends, the distributivity ends. So 5x is going to multiply 6x. 5x is going to multiply negative 7. Bracket ends. That's it for stuff being multiplied by 5x. This 5x here is not going to multiply anything past the end of that bracket. Okay, let's set it up. So 5x times 6x, I'm going to show that. 5x times negative 7, so plus 5x times negative 7. Some people prefer to write this minus 5x times positive 7. If you prefer that, that is totally fine as well. And then we'll do this part. And here, really important to remember, this minus sign goes with the x. So anytime something is getting multiplied by the x, it's actually getting multiplied by negative x or minus x. So we'll do minus x times 5x minus x. And this is the negative sign people forget, right? They just look, they're like, oh yeah, x times 2. It's not x, it's negative x. So negative x times 2, and there we go. So now we can see all the multiplications we need to do. 5 times 6 is 30. X times x is x squared. 5 times negative 7 is negative 35. The x doesn't have any other variable, so it just stays x. Negative x times 5x, well, this is like negative 1, right? I can write that 1 in there. Negative 1 times 5 is negative 5. X to the power of 1 times x to the power of 1 is x squared, minus x times 2, well, that's just 2x. So at this point, I'm finished with distributivity, but I'm not actually done with simplifying. It's had as much simplifying with distributivity as possible, but there's like terms still left. Here's an x squared term, here's another x squared term. This is an x term, here's another x term. So I want to gather my like terms. 30x squared minus 5x squared is 25x squared. Negative 35x minus 2x is negative 37x. Oh, hopefully the autofocus works. Yep, there we go. And so you can see here we took this pretty complicated situation at the beginning. We had lots of brackets. We had 1, 2, 3, 4, 5, 6 different pieces to it. And we've got it down to just 2 terms, no brackets, much simpler. If you ever want to check your work when you're doing these, say you get to the end of a test and you have a bit of extra time, the easiest way to do that is to just substitute in a number, preferably not 1. I usually pick 2. 1 sometimes doesn't work out very well, but 2 usually works really well. So I can substitute it into the original and into the final and make sure they calculate the same thing, because that's our goal when we're simplifying, is to get a new expression that always gives the same values as the original expression. So let's check it with 2. 5 times 2, that's 10. 6 times 2, that's 12, minus 7. Minus 2 times 5 times 2 is 10, plus 2. Okay, so 12 minus 7 is 5. 10 times 5, that's 50. 10 plus 2 is 12. 2 times 12 is 24. And finally, 50 minus 24 is 26. So when I substitute in 2 in my original, I get 26. If I substitute in 2 here, I should also get 26. So let's see, 2 squared is 4. So this is going to be 25 times 4, minus 37 times 2. Now, and you might not be able to see that, so I apologize. I'll write the next one bigger. So 25 times 4, because 2 squared is 4, that's 100. 37 times 2 is 74. 100 minus 74 is indeed 26. And so you can see that our simplified expression gives us the same value, 26, as our original expression if we sub in the same x. Seeing a question from Jackson, is there a way to add exponents on Google Docs? Yes, there are 2 different ways. So if you're just normal text in Google Docs, so you just do 2x and then you want to do squared, just write 2x2, highlight the 2 and go to Format, Text, Superscript. So that's the Format menu, Text, and then Superscript. It has a shortcut key, which is Control period. For some reason on my Chromebook, this shortcut key doesn't work. On most computers it does, and in fact, it's the shortcut key in most editors. So if you have Microsoft Word instead of Google Docs or something else, the Insert menu in Google Docs, and halfway down it says Equation. then it brings up a whole new bar of options. And in the second last one, called math operations, at the end of the first row is the exponent option. And so you can use that to create exponents as well. And that's usually how I do them when I'm making documents for you. So hope that helps, Jackson. Try it out and let me know if that gives you any issue. All right. So we've got that set out. If you can type a 1 in the chat if you're feeling comfortable with this stuff, and type a 2 in the chat if you have more questions. And Donut Destroyer, I see you've got a question. We'll get to that one in just one moment. Okay, Emma. All right. So I'm going to do one more example, Donut Destroyer. I'm going to give you an example of how to do this. If you can just tell me, did you see any of the earlier examples, or is this your first example? And if it's your first one, then I'll give you one that's slightly easier. We just did a super complicated one here. All right. So I'm not seeing an answer, so I'm just going to go ahead and do one last example. And that is to look at 7x cubed. First example. Okay, thanks, Donut Destroyer. So we'll give you one that's a little bit easier to do here, times 3x squared. And I'm also going to make it a little different than anything we've seen so far. Plus 2x minus 6. Oh, thank you, Jordan. There we go. Okay, so this one's a little different than anything we've seen so far because now there's 3 different terms inside the brackets here, not just 2 terms like all the ones we've seen. Front, now it's a monomial, not just a regular number like the previous distributivities that we did. But it still follows the same rule that whatever's out front multiplies each term inside the brackets. So I'm going to show that multiplication here. 7x cubed, the second term, 2x, plus 7x cubed multiplies the third term, negative x. So that's the multiplications that we're going to have to do. Some people like to draw arcs over top. You're welcome to do whichever way works best for you. Okay. So now we're going to do each of these individual multiplications. We have 7 times x cubed times 3 times x squared. Because it's a big multiplication, we can change the order however we want, because it doesn't matter what order you do multiplication in. So 7 times 3 is an easy one, so we'll do that one first. That's 21. And then x cubed times x squared, our exponent laws say if we multiply 2 powers with the same base, we're going to add the exponents. So we'll get x to the power of 5. 3 plus 2 is 5. We'll do the same for the next term. So 7 times 2 is 14. X cubed times x, well, x is like invisible x to the 1. So when we go to add the exponents, we're going to get 4. A lot of people forget this, or they think it's like a 0 there. It's not a 0. X to the power of 1 means a single x all by itself, and that's what this is if there's no exponent. And then we'll deal with the last one, 7 times negative 6. Oh, that's not positive. That is negative 42. And then x cubed, there's nothing to multiply it by. So we just have x cubed. At this point, we look if there are any like terms to collect, but there aren't. This term has an x to the 5, this has an x to the 4, this has an x to the 3. Because the exponents are different, then they're not like terms. All right. So if you wouldn't mind leaving the stream open for another minute or so, I'll take any questions that are there. And if I don't get any questions in the next minute, then we'll end the stream. Thanks so much for coming out today, folks. It was really nice to have a little bit of interaction. Good question, Jordan. So in the textbook or in the Google Classroom, where the day 14 post is, if you go in there under the instructions, it has the numbers. So it says page 322, questions 1, 4, 10, 12, 15, 16, 18, 20, 21, 28, 32, 34, 35. You'll find these are really, really fast to do. And I didn't want to just assign 1 through 35, so that's why the list seems so long. If I'd written just do 1 to 35, it would seem shorter, but I think you'll find it's pretty quick to do. And that's posted in the Google Classroom. Nina, instead of writing the second sentence, can I just automatically multiply it and get the answer? Absolutely. That is totally a reasonable way to do things, Nina. Just make sure that you're checking your work carefully if you do that, because it's easier to make mistakes if you don't show that middle step. Hi, Josh. All right, Jordan, excellent. Glad that worked out. Okay, folks, I think that's it for questions. Thanks so much for staying on the stream to make sure everyone could get their questions answered, and we'll chat again on Monday. Take care.